Welcome to this video, everyone. So in this video the scene is little bit changed. So once again we have a primal problem, which is maximize z equal to this objective function and subject to these two constraints are given. uh, just to note, it's a maximization problem. The first constraint is in the lesser equal to form, so this is all right. But the second constraint is not of lesser equal to, but it is of equal to type. So we have to deal with this problem a little bit differently. So first of all the inequality, all the constraints should be of inequality type. So we have to convert into its inequality form. So let us see how we can do that. So first, from that problem, we so just writing the constraints now. The first constraint remains the same, whereas the second constraint we can break this into two parts. So number one is x1 minus 2x2 plus 4x3 lesser equal to 3 lesser equal to 3, and three x1 minus 2x2 plus 4x3 greater equal to 3. See how it's happening. So whenever we have a is equal to b, we can always write both of them to be like this, because these two are equivalent. Basically these two are equivalent, because whenever a is greater equal to b and a is lesser equal to b at the same time, then there is no other option than getting that a is equal to b. So that's how we break this constraint into two parts, and then just write x1, x2 and x3 greater equal to 0. Now in the previous video I have told you that in case of a maximization problem, all the constraints should be of lesser equal to type. But in this problem there is one constraint which is not of lesser equal to type, but it's of greater equal to type. So how we deal it? We multiply both sides by negative sign, and as a result this constraint will also become a lesser equal to constraint. So how we do it? We multiply both of them with positive sign, with negative, and this is yes, and therefore this inequality will be changed to lesser equal to. This side also we have a negative 3. So what we have done? We have just multiplied the constraint which was of greater than or equal to type by negative 1, basically negative 1 multiplying by negative 1, so that we obtain all the constraints as lesser equal to form. Now we are good to go. So we have three constraints. So corresponding to that, just like the previous problem, we will introduce three decision variables for the dual problem. So the new problem will be of minimization, because here we have a maximization problem. So minimization, minimize w is equal to the same old story. These constraints, the constants from the constraint equations will be coming, plus 3w2 minus 3w3, and subject to. So we are going to have three different constraints for this. The first constraint corresponding to the decision variable x1, so 2x1 plus 3x, not x1, 2w1 plus 3w2 minus 3w3. Now this time this sign will be of greater than or equal to type, greater than or equal to what? The coefficient of x1. So this constant is with respect to x1. Now coming to the second constraint, we have 3w1 minus 2w2 plus 2w3 greater than or equal to, what is the 10. 10 is the coefficient of x2 in the, and 2w1. I'm not going through this method once again completely, because in the previous video you can see that 4w2 and minus 4w3, which is once again greater than or equal to, let's see, 2. And here we have w1, w2 and w3 greater than or equal to 0. Now let's look at the problem 1. This is the dual of the exact previous primal problem that we had converted, but let's look at the actual problem. In the actual problem, how many variables we have? Sorry, how many constraints we have? We have two constraints here. So if we have two constraints here, in the dual problem also we are supposed to have only two dual variables. We are only supposed to have two dual variables. So now see, we are going to convert this whole problem with two only. See what happens. Consider this w1. Let us introduce some new variables. y1 is equal to w1 and y2 is equal to w2 minus w3. y2 is equal to w2 minus w3, and we will call this w, you can keep it as it is, or whatever. These are just for nomenclature. Now what happens, if you look closely, you will be able to see why I have taken this, because everywhere you can actually take this w2 minus w3 out everywhere. So let's write down. Okay, I will write this in detail. Plus, see, we have 3w2 minus 3w3, so this can be written as like 3 into w2 minus w3, or I can just write 3y2. Now we have subject to, once again this same story will be repeating, 2y1 plus 3y2 obviously. Then we have 3y1 minus 2y2 greater or equal to 10, and finally 2y1 plus 4y2 greater or equal to 2. Now the story is like, what is the main difference? The difference is that, see, here you had w1, w2, w3 all are greater or equal to 0. But when we convert back like this, then obviously y1 will be greater or equal to 0, but this y2, this becomes y2, we cannot specify its sign now. y2 is unrestricted in sign. y2 is unrestricted in sign. So this is how we deal with this problem. So what we have done from the beginning, let's see first. See, if there is an equality sign, now the variable corresponding to this will be of unrestricted sign. Now how we have done it? First we have converted into all less or equal to sign. Then we have converted to dual. Basically we have found the dual variable, and then we have combined two variables to one variable so that that particular variable becomes unrestricted in sign. So this is the end of this video. Thank you.